won't be exact, but it'll be close. And you can imagine, well, maybe this is how many rectangles? 1, 2, 3, 4, 5, 6, 7, 8, 9. I could say, maybe I want, 9 is too much. I just want 3. So I could take these 3 and say, well, let's cross here and here. Right? And then another 3, maybe we go there, and another 3 goes over there. So the third, right? I combine these. I'll still get an approximation, but it won't be as close. Or I could take these and say, can you make it even smaller? Can you cut the rectangle even thinner and have more of them? Well, then each one is going to be close. There'll be less of this extra on each side that I'm not sure, right? I get a thin one here, another, and I add them up. Now you can imagine doing this until you have tiny, tiny rectangles and you have infinitely many between here and here. If you had infinitely many rectangles and they were infinitesimally small, narrow, then you would probably have a very good approximation to the area. And that's how we approach doing it. So this process of making things, so with the derivative, with the slope of the tangent line, is that if I take these secant lines and I bring them closer and closer and closer, to here, the blue line, we have this curve, right? And I want to know what is the slope of the tangent line at A. There's a blue line. The blue line doesn't touch the blue curve anywhere except A. So I don't know how to get this slope. Why? Because there's no point to this way. But I can do secant. I can go from A to somewhere else on the line, and then I can bring this point closer and closer and closer. And the closer I get, the more these secant lines become close to the tangent. And now you can imagine, if I could keep going closer and closer and closer infinitely far, I'd probably get to the right answer. So that's taking a limit. This isn't the precise mathematical definition of the limit. We'll get to that later. But the concept of the limit is you do something that gets smaller and smaller and smaller and smaller until you get close to it. And the same thing with the area. Except in this case, we're making the rectangle smaller and smaller and smaller and getting more and more. We want to know. So if I calculate this area, the out of all these rectangles, we get a number. If I divide them in two, and I line them up, and I add up the area, I get another number. If I divide those again in two, and I 4 times the linear rectangle, and I add up the area, I get another number. And those numbers should get closer and closer to the right number. That's taking the limit. Okay. So, this is just more motivation. Calculus, of course, is more than just, that's all that calculus is. I just said you take limits of secant lines to get the slope of the tangent, and you take limits of rectangles to get the area. What's all the fun? Not so much talk about calculus. Those are the basic tools of calculus. Those are the initial questions. But calculus then opened up to many more things. So for example, when we have been talking, we've only talked about a function of one variable, f of x. But you can have functions of more than one variable. You can have f of x and y. So you say there's an x-axis and there's a y-axis, and now the answer is a z-axis. So now we're in 3 dimensions. Yes? What's that one in that case? This is an introduction to calculus. preview of what we're going to learn. We haven't touched anything yet. No, we can touch anything. With the love. Normally, these ideas of the slope of the line, that should be familiar to the previous courses. So here, as examples, we might want to know, so when planes fly through the air, or when satellites go around the Earth, we're moving in 3 dimensions. The plane has a certain height above the ground, but it's not just moving along one line, it can go left, right, go up, down. So where it is a function of many variables. Similarly with this. So now calculus expands. How do I understand this multiple? Well, there are multivariables. So we have multivariable calculus, which would be a later course. But it's very useful for many different applications. This is a great book to do this exercise. So you can review just these exercises to go over the concept again and really make sure that you've understood them well. Yes. So that's another challenge. I shared it with the professor. I'll create a group for the class. So the course outline. I'll also, the course outline is also on the Moodle. You know where you submit your assignment online? No. The portal? Yeah. So the course page will also have these. By the way, if you don't know, there's a phone app for that platform. It's much easier to use. You don't need it. Oh, you have it? Yeah. The textbook is not there yet, of course. Okay, so these are the top of exercises to test your understanding. But let's move on to the concept of the limit. So maybe one of you can just read the first paragraph.
The concept of limit or limit interval is influence. The concept of a limit or limit interval, essentially the understanding of calculus, has been around for thousands of years. In fact, every mathematician used a limit interval to obtain creation and later approximations of areas of the curve. Yet the formal definition of a limit has been lost and understanding today. Did not appear until the late 19th century. We therefore begin our quest to understand limits, as our mathematical ancestors did by using an intuitive approach. At the end of this chapter, I'm looking at conceptual understanding of limits. We examine the formal definition of a limit. We begin our exploration of limits by taking a look at the class of the function. Function of x is equal to x1 minus 4 divided by x minus 2. Then g of x is equal to that of x. Is that of x?
No. Do you know your straight lines? No good. So two straight lines on either side is absolute value. You go from absolute value? Absolute value? What is absolute value?
The alternative is has the opposite.
Yeah. So the absolute value takes whatever is inside and makes it a positive. goes here. But if it was negative, it becomes 1. Right? So if you have, if I ask what is the absolute value of 3, you tell me. So let's see. Here. So there's the absolute value of 1. What is the absolute value of a million? What is the absolute value of 95? What is the 5? You can equate anything negative. So x minus 2, the absolute g of x is the absolute value of x minus 2 divided by x minus 2. Now, you might say, well, that's just minus 2 divided by x minus 2. That's not much. The absolute value makes a difference. And then, and h of x is 1 over x minus 2 squared. So this is the exponents, 2 and 3, which is squared, cubed, and then to the 4th to the 5th. And these are shown in these figures below. So, in each of these, we can look at the behavior of each graph. Right? Oh, so you said, what is intuitive? Intuitive is, how do you explain intuitive? You just have a feel for what is the right thing. My intuition tells me I should go this way, not that way. I'm walking through the woods and I don't have a map, and I don't know, I've never been, but I think I should go this way. So when I have an idea, I have a certain understanding. It's not exact, it's not scientific, I can't explain to you exactly why it is, but I have a sense. So here, an intuitive approach is where we're going to start, not by very formal lessons. There is a formal definition of limit, which we will get to. But for now, we just want to get a feel for it. And it's very easy to get it. Limits are a very simple thing, actually. So here are these 3 graphs. Okay? Of these 3 functions that we just said. So one of them looks like a line, and it has this dot, this circle, open circle in the middle. Do you remember what an open circle is? It means this point is excluded. Right? It means that x equals 2, there's no value. Right? F of x, when x equals 2, we put it inside, right? If x equals 2, what is f of x? We would have 2 squared, which is 2 squared, which is 4. So we'll go that one, 2 squared. 2 to the power 2 is 2 times 2. So multiply it by 4 minus 4, which is 0. There's 0 on top, divided by x minus 2. So x is 2. 2 minus 2 is 0. Now we have 0 divided by 0. That's not defined. So f of x has no value at this point. Right? It's not 0, it's not infinity, it's not anything else. It just does not have a value. Everywhere else, you can put a number for x, and you get another number. You get the f of x. Right? So there's a line. This is all of the f of x, except here. There's no value. So that's one kind of scenario. Then we have an example like this one. So remember, so the absolute value of x minus 2 divided by x minus 2. So let's say, suppose x is 3. What is this equal to? So this will be done there. If x is 3, what is this? 3 minus 2, that's 1, absolute value of 1, okay. Divided by 1. 1 divided by 1 is 1. If we put 4, what do we get? 2 divided by 2, which is, again, 1. Oh, it looks like anything I have here is the same thing below. Let's just make sure it's positive. Well, if this is positive and this is positive, then it's something, it'll be 1. So it's 1 forever. But now, if x is less than 2, let's say x is 1. 1 minus 2 is negative 1. So this will also be negative 1. So, but now, I don't have negative 1 divided by negative 1 because this is absolute value. Absolute value negative 1 is 1. 1 divided by negative 1 is negative 1. So I'm down here. And you can, the same idea, you can go to any number. If this is less than 0, and this is also less than 0, you're left at the absolute value. So this is why the absolute value makes a difference. Okay? Now it says, if this is less than, then it's undefined. Now, what about at the point 2? If x is exactly 2. 2 minus 2, 0, find absolute value, 2, 0, divided by x minus 2, 2 minus 2, 0, 0 minus 0 divided by 0 again, that's also not defined. Okay, so here, I can get very close to 2. I still am able to define less than, but very close. Then, it's negative 1. But exactly at 2, there's no value, open source. And the same thing happens. Last example. We have these 2 curves of over. Okay? And the function is h of x is 1 over x minus 2. So what happens? Not really see that. If x is 2, what is this? This is 0. 0 squared is 0. 1 divided by 0. 1 divided by 0. 1 divided by 0. It has an answer. What is that? It's infinity. If you divide by something, when you divide by 0, it's equal to infinity. So, at the point x equals 2, h of x, you can see that it's getting higher and higher and higher. And at 2, you're off the chart. So, it's not equal to a number, when I said it's not undefined. It's not a number, it's infinity. Infinity means bigger than anything. Right? Any number you pick. The number could have 1 million digits. You could write 1 million digits. Right? You could write more digits than the size of the universe. From here all the way to the other side of the universe, you can write digits. Infinity is still bigger than that.
Then why you calculate the bracket as L?
And what?
L. L? Yeah. As you can have error. Like it can't be defined.
Because the calculator only deals with numbers. The calculator doesn't have, so a human mind is more powerful than a computer. Because you can understand things a computer doesn't understand. The computer just manipulates symbols. It manipulates zeros and ones. So there are some computer software, more advanced mathematics software, that if you say something 1 divided by 0, it will tell you this is because it has been programmed to recognize, I have a number divided by 0, that's infinity. By 0 divided by 0, that's 100. So each of these 3 functions is undefined at x equals 2. They don't have a number or value. But here is if all we say is it's undefined at x equals 2, then I'm not giving a very complete picture of how each function behaves, right? This is undefined at x equals 2. This is undefined at x equals 2, and this is undefined at x equals 2. But they're undefined in different ways. These are very different looking graphs. So, in order to describe the behavior of the line, of the functions, equals 2, we need the concept of a limit. Let's take this first one here. If we look at the function on either side of x equals 2, as it gets closer, from here and from here, as they get closer to a number, even though there's no value of x equals 2, it's easy to see that, well, everything's getting closer to the point 4, the value 4. So it looks like from both sides the function is approaching the value 4 at x equals 2. Undefined at x equals 2, but it's approaching 4. How about in this case? Well, from the right and from the left, they're approaching different values. I can't say that this one, everything is approaching that number. Can't say that here. But you can say, well, from the left it's approaching one number, and from the right it's approaching another number. Okay. Here it's getting close to 1. All of this is 1, so that's 1. And down here, if we're going this way, we get closer and closer, minus 1, what is the minus? And in this case, if you get closer and closer to 2, your number, so if you're close, you have a number. The function is defined. It's only undefined at 2. But near 2, it has a value. So the values are getting bigger and bigger and bigger. Very fast. So they're getting infinitely big as you get closer to 2. So these are intuitively, you can say that the limit of f of x as x approaches 2, in the first case, we will say here, the limit of the function as x approaches 2, the limit Alright, and we write it like this. We write it as the limit of f of x as x approaches 2 is 4. That's how you would do it. So, a limit is the limit of a thing as a variable approaches a certain value. What does this approach? If x gets closer to 2, what does this get closer to? In this case, we're saying to the limit of this as x approaches 2, this gets closer to 4. Does that make sense? Does that feel? Yeah. So, I want to just read what it says here. We could go over this again as we go. But here is a bit of a slightly more formal definition. This is not a very precise mathematical definition, but it's our intuitive understanding. So we say if f of x is a function, let f of x be a function defined at all values in an open interval containing a. Do you remember intervals? Yes, open intervals. So we're saying over some portion of the x-axis that contains the point A. So we're interested in some point. A will be this point where we want to know the limit at that point. So if you want to know the limit at the point, you need a function that is defined around that point. There's a possible exception of A itself. But so A of f of x is not defined at A, but it has to be defined everywhere around A. And let L be a real number. You know the different types of numbers? Integers, natural numbers, integers, rationals, and reals. So let L be a real number. If all values of the function f of x approach the real number L, as the values of x, where x is not A, approach the number A, so as x gets close to A, if all the values of f of x approach some number we call L, then we say that the limit of f of x, if x approaches A, which is kind of, so if x approaches A, the limit of f of x, well, we read it as the limit of f of x, if x approaches A, becomes alright. So, one obvious way to estimate limits is you construct a table. And you say, okay, if I have this point A, I can take a little bit less than A, and then get back closer and closer. I can take A minus 0.1. So A is on my x-axis. I take A, I subtract 0.1. And then I say, what is the function, what is the value of f of x at this point, A minus 0.1? Some number. Then I say, now what is it at A minus 0.01, which is less? A minus 0.00, A minus 0.000, and so on. And for each one, we can write down what is the value of the function. We can do the same thing on the other side of A. So this is less than A, all of these are a little bit less than A. All of these are starting a bit bigger than A, but then coming back. Right? You remember from last semester, this is bigger than this, is bigger than this, is bigger than this.
Yeah.
So you're adding something that is getting smaller, which means you're coming in closer and closer to A itself. These are getting closer and closer to 0 as you keep adding. And so you can make the table as short or as long as you need, and it doesn't have to be 0.01. That's one way you can go in different increments. Whatever you can choose. We want to get very close to see if there's a pattern. We're looking for a pattern. So for example, here's one. Here's a new function. So the question is, evaluate the limit of sin of x over x as x approaches 0 using a table of functional numbers. Okay, sin of x over x. So if x is around 0, if I say 0 minus 0.1 is minus 0.1. So at minus 0.1, this function has a value of 0.9983416666. Alright. Now I get a bit, 0.1 was, this is 0. 0.1 is maybe out here, right? 1 is over there, here's close on. Now I go minus 0.0 over there. So instead of here, I'm now at 10 times closer. And here, the value of sin of x over x, if x has this value, is 0.9999832241. And I take even 10 times closer again to here. 0.999999832241, and so on. Do we see a pattern? What is the pattern? Are these numbers getting closer to something? What is that number? Right? Let's check on the other side. So this is coming in from the left, right? These are less than 0. Now we start from the right and we get closer. So we do the same thing, right? Again. So what is the pattern this time? What number are we going to do this to? Okay, so it's getting closer to 1, both from the right and from the left. So here we could conclude that the limit of sin of x over x as x approaches 0 is 1. That's it. looks like, sine of x over x. And we were asking, it's not defined at 0, right? But it is defined everywhere around 0. Okay, cannot be defined at the point itself, because we want the limit, which would have to be defined everywhere around it. Okay, so that's all right, condition is met. And if you look at it, you say, oh yeah, all of the numbers do seem to be getting closer to 1. So this confirms the estimate of the table. So one way to intuitively, is you can make a table and see what number are they getting closer to, and that gives you a way of getting an answer. Or if you can get a graph, and for this, computers will definitely help you with it and useful. You can look at it and see, it looks like it's getting close to that number. Again, this is not the rigorous mathematical way that we're trying to get an idea. So here's another example of a different function. The function is square root of x minus 2 divided by x minus 4. And the question is, as x approaches 4 in this case, what is the limit? So at the point 4, first of all, this is not defined. So let's see, to show the square root of 4 is 2 minus 2 is 0, divided by 4 minus 4 is 0. We have 0 divided by 0, not defined. But is my function approaching the value at x? As x approaches 4. So we say, okay, let's say x is 3.9. 9. Are these values of the function approaching? Yeah. What number is approaching? Huh? Can you say 1? Can you say 1? Are these numbers getting close to 1? What would you say? What do they look like? Yeah. 0.3. How about on this side? Are they getting closer to 0.2? Here, are the numbers getting smaller or bigger? As you get closer to 4, are these numbers getting smaller or bigger? Bigger? Well, okay, so why are they getting smaller? Why do you think they're getting bigger? Is it adding more numbers or reducing numbers? You mean it's getting longer and shorter?
From there.
So where is it?
Yeah.
Which one is it? This is bigger? Wow. So how do we tell if two numbers are bigger or smaller? And it doesn't look like. And we say, okay, this is the 10th. And they have the same number, 2. So they're 5. 1, 0. 1 is more than 0. Yeah. So we have, these are now the thousands. So I have 1,000, I have no thousands. Then I have 10,000. But I can only have 9 10,000, and that's less than 1,000. So anything after this is less than 1. If this is a 0, that's a 1, and this is a 0 number. Doesn't matter what comes out. As soon as you get a difference, the one with the bigger digit is the bigger number. Anytime you read a number from left to right, even if the decimal is huge, it was 25, 50 million, 15,000, and 50 million, 1,063. Well, the 15,000 is bigger than the 1,000. They both have the 250 million, so that's the same. The 15,000 is more than 1,000. So that's a big number. Just because I move the decimal here, it doesn't change the logic. So you still read it from left to right, and as soon as you see a difference, you say which one is the higher number, bigger number. So then these numbers are getting smaller. So they can't, if this is already 0.25, if they're getting smaller, they're not going to reach 0.3. But they're getting smaller. It looks like we're getting more zeros in here. This is staying the same. So maybe they're getting close to 0.25. That's from getting closer to 4 from this side. Now we say, when you're getting closer to 4 from this side, so 4.1, 4.41, 4.01, even like that. They started at 2.48. Now the numbers are getting bigger. So we go 2, 4, 2, 4, 8, 9. Ah, 9 is bigger than 8. So this number is bigger than 9. Alright, let's do this. 2, 3, 4, 4, 9, 9, 10, 8, 9. Ah, this one is bigger than 1. And then this one here, 9 is bigger than 8. 9 is bigger than 8. It looks like it's pushing the numbers back. So this one is getting bigger, but it's just adding 9. Right? It doesn't look like it's going to cross. Right? But you keep that, it's getting closer to 0.25. So maybe in this case, the limit as x approaches 4 is 0.25, or a quarter. So let's see. And that's what the text also says. After inspecting the table, we see the functional values less than 4 are decreasing towards 0.25, and the values that were greater than 4 are increasing toward 0.25. So we conclude that the limit, the square root of x minus 2 over x minus 4, as x approaches 4, is 0.25. You can confirm this estimate by looking at a graph of the function. So here we're graphing as a function of x. Here is this function here. And it looks like this, except it's not defined at x equals 4. But it does look like the numbers are approaching 0.25. Let me start. Do you know what this is here? This means I'm kind of squishing I'm squishing part of the axis behind. Because from here to here, if this is 0.25, then this should be 0.25 plus 0.25, this should be 0.5. And then 0.75, and 1, and 1.25, that's how it should be normally. But here we have 0.25 and 3, 3,000, so it's going up in 0.0. But if I did 0.05 from 0, I would have lots of 0.25 would be up here. So I kind of want to bring down, I want to show you the upper part of the graph. I want to hide this part between 0 and 0.25. So I think this is anyway. I can do the same on the other side. So you can put it anywhere on the axis where you want to hide part of the axis. So we have to imagine that normally we would stretch it up, but for the purpose of visualizing it, I'm going to So, this is the sense of what the limit is. So we can see from the table of values, you can see, well, yeah, it looks like they're getting closer to this number. You can look at a graph and say, yep, it looks like it's getting closer to that number. So that's the sense of what the graph is. So there's an example you can do for yourself. This example of the limit 1 over x minus 1 divided by x minus 1 as x approaches 1. Find what is the value and then you can try graphing it. So, as the book points out, it's usually easier if you can graph a function. It's probably easier to see the limit from the graph than by doing table values. But that's not always possible to do. So this next example is clearly using a graph. So here's the function g of x, and you will notice that this is an interesting case, actually. So at the point, so the function is defined everywhere. It's even defined at x minus 5. What is the value of g of minus 1? Is what?
G.
So next is minus 1. What is it? G. Look at the graph. X is minus 1. When we say g of minus 1, when we put it in minus 1, so this is back to x. If I put in here minus 1, then I'm saying when x is minus 1 here, then what is the value of the function? So then we will find a full dot is the value. An open dot is no value. The full dot, and the value is 4. The function is defined, it has a value is 4. So when you look at the graph, you say, what would be the limit as x approaches minus 1? What would be the limit of g of x? Okay? What do all the values of g of x, what value are they approaching as x gets closer to minus 1? So if you go along the curve, you get closer and closer to minus 1, right? You're getting close to 3. So notice you can have a limit that is different from the value of the function. And as it points out, note that we can determine this limit without even knowing the algebraic expression of the function. I haven't told you what g of x is. I haven't said g of x is x cubed 3 minus, right? We don't know what the algebraic expression is. We just know this is the graph of the function. And just knowing the graph, we can find the limit. By looking at graphs, you can find out. So we now know two techniques for finding the limit. One is, if you have the algebraic expression, you can make a table of values. You can see what the values are close to. The second technique is to look at the graph. And see, if I get close to that point, if I follow the line, the curve, what does it get close to? So this is what I just said. Based on this example, we can make an observation that it is possible for the limit of the function to exist at a point, and for the function to be defined at a point, but the two have different values. So the example we just saw, the function value was 4, while the limit was 2. So we'll have to find the different values. It's possible. Nothing very common. No, it doesn't. But it's possible. Okay. Now, so we want to look at a few important, for the laws of limits. So there are laws for how limits can be, how you calculate limits. So we want to be able to find it. The reason we want to find limits is it will help us to find the limits. derivatives are defined in terms of that. So we need to understand what we're doing about that. So the first two laws are very straightforward. So the first law says, if A is a real number and C is a constant. You know what that means? So if the limit of x as x approaches A, and A is what? A is a real number. So the limit of x is just a straight line, to 0. So if, and that's defined everywhere. So if x approaches A, what is the limit for that? It's just A. So the first limit of this one is easy to see that, so the function f of x is just x. So as x approaches A, f of x, which is also x, f of x is also going to go with A, so the limit is x. In this case, it's kind of a constant. My function is a constant. You know what the graph is to look like. F of x is a constant. What does that look like? It would be a straight flat line. So it doesn't depend on x. I can have any x value I want. F of x is just that. C is 3, then for line y equals 3. For any x, my function equals 3. So the limit of the function that is constant as x approaches anything is just that. So those are the first two laws. Now we need to consider a possibility, which is sometimes the limit does not exist. Not always the case of a function. We can be a function, remember, perfectly well-defined function, that does not have a limit. The limit does not exist. So we remember the definition of the limit was our intuitive definition of the limit was this. We said, as x approaches A, if all the values of f of x around A are getting close to the same number, L, then L is the limit. But what happens if, as you get closer to A, the values of the function are not approaching one number. They're jumping around. So you see an example where it jumps around, and therefore the limit is not. There is no function. And that's also possible. So here, so now we look at the function with a sine of 1 over x. This function, what is the limit of the sine of 1 over x as x approaches 0? So one way of doing it is we can look at a table of values, and we can look at big numbers that get smaller and smaller, getting closer and closer to 0, and you'll notice we started at 0.5, smaller point. Well, now it's minus 0.8, we jump down. Back up to 0.3. Minus 0.03, which is 0. Up to 0.3, almost to 5. it's just similar, but with the opposite sign on the other side. This is not getting close to a particular number. It's not clear to that number. It doesn't mean it doesn't happen. Maybe I have to start even closer. Maybe it's doing something really wild, but when you get closer, then it gets close to a number. So this table has not helped us yet to find out if there is a limit and it's still over 8 feet. So we're not approaching any one particular value. But before we can conclude in math, we want to be able to have a logical, to really be sure by having this is true of the manuscripts. So we say, well, these values are not approaching anything. So it looks like there's no limit. It seems there's no limit. But before we can say that for sure, maybe we can find an even better argument to show why there is no limit. And one way to look at, for this particular function, right, sine of omega x. So we know that sine is a periodic function, right? It's the one that goes like this, it goes beautiful, and it starts at 0, it goes up to 1, back to 0, minus 1, back to 0, up to 1, back to 0, and it just keeps doing that. And the point where it hits the 0 is at 0, pi, 2 pi, 3 pi, 4 pi. And in between, where it gets to the value 1, that's pi divided by 2. And then it goes to pi, and 3 pi divided by 2 is minus 1. And 2 pi, 5 pi divided by 2 is 6 pi divided by 2, 3 pi, 7 pi divided by 2, 8, 9. So it's a multiple, right? It's periodic. It repeats itself. So now let's think about, well, okay, I know it repeats itself. So what happens on each of those repeats with x? So if x is now this is 1 over x. So if x is 2 over pi, 1 divided by 2 over pi, well, we know that if you divide this, then it's like I can split x. Right? So sine will be 1 over this is pi divided by 2. I know sine of pi divided by 2, that's just 1. That's the top of the first curve. Right? You want that? Yeah. So that's 1. Now 3, if x is 2 divided by 3 pi, well, that'll get flipped in here because it's 1 over x, and sine of 3 pi divided by 2. Well, that's easy. I know that too. That's when it gets down here. And down here it's what? So it's minus. Okay. So remember my s curve, my sine curve goes up to 1, and then down to minus 1, and then so that'll be minus 1. The value of the function when x is this will be minus 1. And when x is this, it will be 1 again. The next up, and then the next down, and then the next up, and then the next down. So I'm going 1, minus 1, 1, minus 1, 1, minus 1. And I can keep doing this for now, here, these values of x are 2 divided by pi, 3 pi, 5 pi, 7 pi, 9 pi, 11 pi. I'm dividing by a bigger and bigger number. What happens if you're dividing by a bigger and bigger number, then this is getting smaller and smaller. So the x's are getting smaller, which means they're getting closer to 0. Right? They're getting closer to 0, but as they're getting, I can go as far as I want. I can make this very, very close to 0. And I'm still going to have 1, minus 1, 1, minus 1, minus 1. So it looks like this function, as it gets close to 0, it just starts bouncing faster and faster and faster. And it does not approach any number. So if you look at a
little bit of nomenclature.
At this point, we can indeed conclude, based on this argument, that the limit of sine of 1 over x as x approaches 0 does not exist. And mathematicians frequently abbreviate does not exist as VNE. So if you see capital VNE, means does not exist. Remember that. So we would write the limit of the sine 1 over x as x approaches 0, VNE does not exist. Not equal to anything, it does not exist. And this is the graph. So you can see that as you go farther in x, you get the slower and slower, more and more stretched out. The farther you go, the more stretched out. But the closer you get to 0, the more compressed it becomes. It starts oscillating faster and faster and faster. And it's not approaching any particular number. So here, this is not exist. There is no limit. Okay. This doesn't take much, this will be obvious. Once we understand that there are limits, here. So you might have a function like this, for example. So you remember the very first we had those 3 examples of the means, and one of them was 1 and then minus 1. So it had a limit from this side, the limit was like it was 1, but from the left it was minus 1. So we talked about, so far we talked about two-sided limit, the limit that is coming from both sides. Which are called two-sided limits. We also have one-sided limit. A function can have a limit coming from one side, from the positive numbers, from the bigger numbers getting closer, and from the right getting closer, and that limit can have one value. And from the left getting closer, it can have a different value. And there is no one limit. We can't just say the function has this limit. It has no two-sided limit. If you just say the limit of the function, implicitly it means the two-sided limit, the full limit. But sometimes the function doesn't have a limit, the same limit from both sides. But it does have a limit if you only come from one side. It might also have a limit if you only come from the other side. You can have one, or the other, or both, and they may be different. When the two sides, the one-sided limit from the right and the one-sided limit from the left, are the same, then we say the function has a limit to two sides. Make sense? Yeah. Good. Now we need to go over that. So in this case, what would the limit at x equals 2 mean? So each of these marks is 1 unit. If there are no numbers given, you can always assume that it's 1, 2, 3, 4, 1, 2, 3, 4. So what is the limit at x equals 2? What is the limit at x? What is the limit of the function as x approaches 2? So this is important. A limit is not at the function. The limit is as x approaches that.
So we're looking at those two equations, x plus 1 and x squared minus 4. Or
It doesn't matter what this is. Well, you can look at it if you like. Yeah. This is the graph of this function. This is called a piecewise defined function. There's a peak less than 2, I define it this way. And there's a peak if x is equal or greater to 2, that has a different